Welcome back, everybody. In this video, we'll be starting chapter 3. As is always a good idea to take a look at the chapter, see what it is we're getting into before we get into it. In chapter 3, it's about polynomial and rational functions. There's a total of 9 sections in the chapter, although we're only going to cover sections 3.1 through 3.7. Overall, the section is about looking at a new kind or class of functions called polynomials, which we've already actually seen before, but this chapter deals with them in more generality. We'll be looking at how to solve polynomial equations and how to graph polynomials. And part of what 3.1 is about, where we'll start, is about introducing the set of complex numbers, which are going to help us describe the solutions of polynomial equations. 3.2, we'll look at quadratic functions and the quadratic formula kind of over again, in case you've never seen it before. 3.3 is more theory about polynomial functions, and then power functions, which are a particular kind of polynomial functions. 3.4 focuses on graphs specifically. 3.5 is about division, which is going to give us some tools that will help us in the next section. 3.6, which is about zeros of polynomial functions. So in a way, an easy way to describe what this is about is you're probably familiar, you may have forgotten the specifics, but you're probably familiar somewhat with the quadratic formula, which is used to find the solutions to any degree 2 equation, right? Any quadratic equation. So what this chapter is about trying to find the solutions for equations that have higher degree. And we're able to do that for certain kinds. 3.7 is about rational functions, which is basically like functions whose form is that they're quotients of polynomials. So an example of a polynomial would be, or a quotient function would be x squared minus 1 over x plus 3. Okay, that would be an example of a rational function. So this is the chapter we're working on now. In this video, we're just getting started by taking a look at complex numbers. So the big idea is this. An equation that looks like this, x squared equals -4, doesn't have a real number solution. As you know, whenever we square a negative number, we get a positive answer. And if you square a positive number, you get a positive answer. So if we write x squared equals -4, this seems to imply that we've got this number x that we could square, and we would get a negative number 4 out of it. And it's true that there's no real number solutions for this equation. So what we're going to do is make a definition of a new number that will help us come up with a solution for this. So we're going to define the imaginary unit I. Okay, and it's going to be equal to the square root of -1. Okay, when we say imaginary unit, by the way, when we say unit there, unit has more in the sense of one, like unity or united, not unit like feet, inches, and miles, and gallons and stuff. It's not that sense of the word unit. It's more unit as in one. And so we're defining this thing called I, and it's the square root of -1, basically by definition. And so if we have this thing called I, which is the square root of -1, then we can take two of them, take 2i and square it, more on this later, and say, okay, well, this would be the same as 2 squared I squared. That's 4i squared, just using our usual rules of algebra and working with exponents. And say, okay, well, if I is the square root of -1, then I squared would have to be -1. So we're defining this number that is saying, okay, well, if we square it, we're getting -1. So 4i squared equals 4 times -1, or -4. So in the end, this equation, x squared equals -4, has solution to I. What's I? I is the square root of -1. Well, of course, there's more to it than this, but that's the basic idea for this section, defining this new set of numbers that we can use to allow us to have square roots of negative numbers and other things. If it seems weird at first that we can just go around defining a new number, okay, if we can't find the answer, let's just define a new number. If it seems weird, we do actually have a history of doing such things. It's just been a while perhaps since we've done that. If you think back to like your grade school days, of course, back then we didn't use X's, we had little boxes. We asked you numbers or questions like this. If you have some number and add 2 to it, you get 5. Right? When you're a little kid, you say, okay, well, it's got to be 3. Okay, 3 plus 2 is equal to 5. Great. But at that time, when you're first learning about numbers and things, if we said, okay, some number plus 5 is equal to 2, okay, well, that's impossible if you don't have negative numbers, right? Because if you're just restricted to counting on your fingers, you can't do that, right? There's no positive number solution to that equation. So what we do is say, okay, well, there's these things called negative numbers that you can use, and there's this number line, and we can extend the number line to the left of 0 and have all these negative numbers. And so there's this number called -3 that is the opposite of 3, and if you put that into that place in that equation, it's going to make it true. So basically what we did is we defined the negative numbers to make up a solution to this equation. That seems more familiar because you're used to it, because it's been a long time since you've been introduced to negative numbers, but we did the same thing there as we did here, just kind of define a new number because we needed it. More recently, probably, the solution to x squared equals 25, well, there are 2 of them, right? -5 and 5 are both solutions of that equation, right? They're 2 numbers that you can square and get 25. How about x squared equals 8? Nah, that's the one that doesn't reduce. X squared equals 7. Okay, what's the solution to that? Square root of 7. Okay, why? Because if you take the square root of 7 and square it, you're going to get 7. So basically, we defined this thing, so now in yellow, we defined this thing to be the solution of this equation because we needed a solution for that equation. So we defined this thing to represent that solution. So the point of all this shown here kind of to the right in the blue is just to kind of illustrate the idea that sometimes we expand the set of numbers that we have to work with to help us be able to solve more equations. Fortunately, there's no more expanding that needs to be done. With the addition of this number I, that's going to be enough for us to solve all the equations that we'll ever need to. Okay, so a couple more definitions. We're defining this thing called a complex number, and it's a number that looks like a plus bi, where a is called the real part of the imaginary number or the complex number. Bi is the imaginary part of the complex number. If b is equal to 0, then a plus bi would be a real number. If a is 0 and b is not 0, then the complex number is imaginary, sometimes called pure imaginary. So there's a lot of words there. Here they didn't write out the part about the imaginary unit, but we've done it. So a lot of words here. So good to see examples for each of these. So here's some examples of some complex numbers. 3 minus 4i, 1/2 plus 7i, 0.4 plus 2i are all examples of complex numbers. Also, if you want to think about 0 plus 3i, which is just 3i, that's an example of an imaginary number, or sometimes called a pure imaginary number. If you have the number 5 plus 0i, which is just 5, then you could think about the fact that all real numbers are actually a subset of all the complex numbers. All the numbers you've been working with all your life up to this point have all been actually complex numbers. They just had 0 for the I part, plus 0i. Okay. Here, let's let z equal 2 plus 3i. Find the real and imaginary parts. So the real part is 2. The way our book is defining it, the imaginary part is 3i. I wanted to caution you here that our book is defining the imaginary part to include the I, but other books, and probably elsewhere online that you may see, the imaginary part is just the 3, not including the I. Okay, but our book, they've chosen to define it as including the I part. So you want to be cautious about that. Okay, so we found the real part and imaginary parts. 5 was pure real, 3I was imaginary. Okay. We can use this idea of an I to help us simplify square roots of negatives from this point forward. So here, this next part is going to use this exponent rule. The square root of AB is equal to square root A, square root B. So we're going to use that right here. Suppose that capital N is some positive number. Then the opposite of N is a negative number. If you want the square root of minus N, which is a negative number, we can write minus N as -1 times N, and that is using this exponent rule. Square root of -1, square root N, and then the square root of -1 by definition is our I, so we'll have I square root N. So we can use that to help us simplify roots like this one. The square root of -16 is the square root of -1 times the square root of 16. Let me put in an intermediate step. -16 is -1 times 16, right? Now we'll use that exponent rule and call that the square root of -1 times the square root of 16. The square root of -1 is I by definition. Square root of 16 is 4. So we'll have I times 4. Usually that's written as 4I. Okay, let's try that again. The square root of -20. I'm going to factor the inside into things I know the perfect square of, like 4, and things that I don't, like the -5. So we'll rewrite the square root of -20 as the square root of 4 times -5. Then applying that exponent rule, we'll have the square root of 4 times the square root of -5. The square root of 4 is 2, and the square root of -5 is going to be this I times the square root of 5. Okay. So there's a couple of different ways this may be written. Some people like to put the I in front of the square root sign. Some people like to put it afterwards. You may see 2 square root 5 times an I. If you do it that way, make sure that you know that the I is not underneath the square root sign, okay? So don't have 2 square root of 5I with the I is underneath. The I is outside of the square root sign, okay? And then here, the square root of -5, how we got that into I root 5, that is the same as -1 times 5 underneath that root sign. And then again, we've turned that into the square root of -1 square root 5. And so that's where our I root 5 came from, okay? All right, so let's try one more of those. Here we have the square root of -25y. And so we'll rewrite that radicand as 25 times -1y. That's the square root of 25, square root of -1, square root of y. So we've applied that radical rule and split this thing into 3 separate radicals. The square root of 25 is a 5. The square root of -1 is an I, and the square root of y is still the square root of y. Okay, and that's that. All right, from now on, we're able to figure out the square root of negative numbers. You're just going to get a complex number result. So from this point forward, at least in this class, you won't want to say, okay, well, it doesn't exist or not a real number or undefined or anything like that. You are able to find the square root of a negative. It's just that it is a non-real number, okay? All right, moving on, we want to take a quick look at how you can visualize complex numbers in the complex plane. So ordinarily, we use just the real number line to express real numbers and an XY plane to represent the relationship between two variables. We can also use the same setup of two intersecting number lines to represent single numbers in a complex plane. So the way that this works is the horizontal axis, normally what you'd think of as the x-axis, is used to represent the real part of a number. And then the vertical axis that you'd normally think of for the y would represent the imaginary part of the number. So to graph a number on the complex plane, for example, z1, which is 2 plus 3i, the real part would be 2 and the imaginary part would be 3. So z1 would be located right here. We would have a real part of 2 and an imaginary part of 3. Similarly, z2, which is -1 plus I, would have a real part of -1 and an negative one, and a imaginary part of +1. So that would be z2. z3 would be 0 plus 2i. So this one has a real part of 0 and an imaginary part of 2i. So z3 would lie along the imaginary axis. Okay, z4 is -4. That would lie on the real number axis. So the real axis is kind of like our regular number line that you've had all your life. We now are just moving off of it in the imaginary direction to plot complex numbers. Okay, so let's see if we can go the other direction. Let's say I have this number z5. See if you can figure out what the real number or the complex number for z5 would be. Okay, well, its real part looks like it's 3. And then its imaginary part looks like it's -2. So this would be 3 minus 2i. Okay, that's it. We don't have a lot of use beyond that for the complex plane, but I wanted to put that out there because we may run across it once in a while. Okay, one thing important to note is that in the complex plane, you need one XY plane for two numbers, or for one complex number, which is built out of two real numbers. So we're not graphing like y as a function of x or something on this. We're graphing a single number, a complex number. It's just that it takes 2 dimensions to do it. Okay, moving along, something that we will have more of a use for is how to do addition and subtraction with complex numbers. And luckily, you're going to find this pretty easy, which is nice. How you do addition and subtraction with complex numbers is basically how you would add polynomials. In short, we're going to combine like terms. So for this one, we have -3 plus 4i. We're going to add to it 2 plus 5i. Adding the real parts first, -3 plus 2. I'll write out all the details on this first one. We'll add together the real parts. And then for the next piece, 4i plus 5i, we're adding together the imaginary parts. So this will give us -1 plus 9i. Okay, so that's it. So we're adding together complex numbers by adding together the real parts and the imaginary parts. If you could look at something like this as -3 plus 4x plus 2 plus 5x and say, okay, let's go back to beginning algebra and combine like terms. If you would find that pretty easy, you're going to find this pretty easy also. We're going to combine the real parts and we're going to combine the imaginary parts. So let's try that 3 more times. So for the real parts, 5 plus 7 is 12. Imaginary parts, -3i plus -2i is -5i. For subtraction, it works similarly, except that you're subtracting the real parts and the imaginary parts. So 6 minus 4 in the real parts, that will give you 2. And then 1i minus 2i is -1i. Make sure you're seeing where all these are coming from. If not, let me know if you have any questions. Last one, real parts. 3 minus 11 is -8. -7i minus another 5i would be -12i. Okay, so that's basically how that goes. You do have to be kind of careful if you're subtracting and there's like a double negative or something, like let's do this one. Okay, so here we have negative 5 plus 2i minus 6 minus 2i. Real parts first. Negative 5 minus 6 is negative 11. So far, so good. And then 2i minus negative 2i. So 2 minus negative 2, that's 2 plus 2, or 4, right? So this will be plus 4i. Okay, so be very careful with those double negatives. Okay, so the rules for addition and subtraction are summarized here using A's, B's, and C's and D's, but basically you see that what we did up here is represented down here. The real parts are added, the imaginary parts are added. For subtraction, the real parts are subtracted, and then the imaginary parts are subtracted. For multiplication, if you had to guess how multiplication is going to go, you're probably right. When we're multiplying together two complex numbers, there are a pair of binomials. And so if you had to go x plus 3 times x minus 5, if I asked you to multiply together those two binomials, you might use like a FOIL method or a distributive property or box method or stacking the two polynomials vertically. However you would do this problem shown up here in purple, you could do the exact same thing to multiply together two complex numbers, because that's really what we're doing, is we're forming the product of binomials. I know a lot of students like FOIL, so I'm going to go ahead and use that for this example. If you're not familiar with that, this is just a mnemonic device or memory aid to help you remember the order of the products. We'll have the first two that we're multiplying together. Then O is for outer. We'll have the outer two will multiply together. And then the inner pair, we'll multiply those together. That's I. And then finally last will be the last ones out of each pair. Okay? That's, like I said, just a memory aid. What's important is that each term in one number gets multiplied by each term in the other. So first, 2 times negative 4 is negative 8. Outers, 2 times 7i is 14i. Inners, 3i times negative 4 is negative 12i. And then lasts, 3i times 7i is going to be 21i squared. Okay, this is the part where something new happens. That I squared, remember, is equal to negative 1. So when you see an I squared, you should replace it by a negative 1. Okay, so let's do that. My negative 8 will stay as is. The two terms, 14i and 12i, we can just combine those, right? 14 minus 12, that will be 2i. And then lastly, we'll have 21 times negative 1. Our I squared became a negative 1. Okay, so this will give us negative 8 plus 2i minus 21. Finally, negative 21 plus negative 8 is negative 29 plus our 2i. Okay, and that will do it for our first multiplication. So in short, we're multiplying kind of like you would multiply two binomials together, only whenever you see an I squared, you're going to replace it by a negative 1. All right, so I'm going to try that on a couple more just to be sure we are okay. Okay, so for this next one, we have 4 plus 11i times 2 minus 3i. So we'll do the firsts first. 4 times 2 is 8. Outers, 4 times negative 3i is negative 12i. For inners, 11i times 2 is 22i. For the last parts, 11i times negative 3i is negative 33i squared. Okay, so now as before, let me just copy over the 8. Negative 12i plus 22i is plus 10i. And then negative 33i squared will be negative 33 times negative 1. That I squared over here becomes a negative 1. So this will give us a plus 33. So that was a positive 8 plus 33 plus 10i. Okay, so that will be 41 plus 10i. Okay, and that will do it. Okay, we have one more. Then we'll look at some division. So for this one, we have 5 plus 3i squared. So remember that that will be 5 plus 3i times 5 plus 3i. We'll do this as we did before. So firsts, 5 times 5 is 25. Outers, 5 times 3i is 15i. For the inners, it's going to be the same, another 15i. And then for last, plus 9i squared. Okay, so that 9i squared is minus 9, right? Negative 9. 25 minus 9 is 16. And then 30i. Okay, this time it was our third one, so I skipped a little of the steps. If you have a question on that, though, let me know. One other thing worth mentioning here is that this thing was not equal to 25 plus 9i squared. Okay, you can't just go through and square the 5 and the 3i. We had to multiply those out using FOIL or some other method like the distributive property. You can't just go through and kind of distribute the exponents. It's true that there is an exponent rule that says if you have a product raised to a power, that you can raise both of the factors to a power. But if you have a sum raised to a power, in general, that's not the same as raising each of the add-ins to a power. Okay, so be careful about that. So we've done addition, subtraction, and multiplication. We're ready to start taking a look at division next. To do division, we need a kind of helper concept, which is the idea of a complex conjugate. So let's see that. Let's let z, it's tradition, by the way, with complex numbers to use z for a complex number. So z will be a plus vi. So real part is a, imaginary part is vi. The complex conjugate of z is written with a little bar on top. So we'd say out loud z bar or z conjugate. And that will be a minus vi. So it has the same real part, but the imaginary part is the opposite of our original number. So here, try some. If z is 5 plus 19i, then z bar will be 5 minus 19i. We keep the real part the same, we change the sign on the imaginary part. For minus 3i, the z bar will be 4 plus 3i. Notice that if it starts out negative in between, it's going to end up positive in between, okay? It just changes sign. Okay, so here, 2 plus 3i, we want to find z times its conjugate. So z times z bar will be 2 plus 3i times 2 minus 3i. Okay, so we're multiplying. One more example of a multiplication. So firsts, 2 times 2 is 4. Outers, 2 times negative 3i is negative 6i. Inners, 2 times positive 3i will be plus 6i. And then finally, we'll have minus 9i squared. Okay, so out front, we have a 4. You'll notice that the outers and inners cancel this time, right? We have negative 6i plus 6i. That adds up to 0. Then we'll have minus 9 times negative 1. 4 plus 9, or 13. Okay, notice that we ended up with a real number answer here, right? There's no I in our final answer. So it turns out that always happens. I'll leave it to you to check that whenever you add a number and its conjugate, you always get a real number. And if you multiply a number by its conjugate, you will always get a real number. Okay, so I'll leave it to you to check that out. Okay. The fact that that turns out to be a real number is actually how we end up doing division with complex numbers, okay? So here, we're going to try it with 4 plus 3i divided by 6 plus I. What you do to do division for a complex number is you multiply the numerator and denominator of this fraction by the conjugate of the denominator. So that will be 6 minus I. Okay, conjugate of the denominator. All right, so let's do one more multiplication. So up top, we have 4 times 6 is 24. For the first, outers, minus 4i. Inners, 3i times 6 is 18i. And then in the back, 3i times minus I, that's minus 3i squared. Okay, I'll simplify that here in a minute. Instead, let's pop down to the bottom. 6 plus I times 6 minus I. 6 times 6 is 36 for our firsts. The outers will be minus 6i. The inners will be plus 6i. Again, notice that those are going to add up to 0. And then in the back, we'll have minus I squared. Okay, a little bit more simplifying to do. So up top, we have 24. Negative 4i plus 18i is 14i. Minus 3i squared, that's plus 3. Why? Because the I squared is negative 1. Negative 1 times negative 3 gives positive 3. Okay, down below, those minus 6i and plus 6i add up to 0. We'll have 36 and then minus I squared. Okay, I squared is itself negative 1. Negative 1, its opposite will be plus 1, so we will have 37. Okay, so let me fill in the steps there. That's 36 minus I squared, 36 minus negative 1, 36 plus 1 is where that 37 came from. Okay, and then to finish, we'll have 27 plus 14i divided by 37. Often, it's kind of customary to separate that into like an a plus bi form. So we'll have 27 over 37 plus 14 over 37i. Okay, the key to getting this done was multiplying the numerator and denominator by the conjugate of that denominator. All right, so let's try that again. For this one, maybe you want to pause the video and try it on your own and then see how we do it together. Okay, so we're going to multiply the numerator and denominator by the conjugate of the denominator we already have. So it's 7 minus 2i that we were given. We'll go 7 plus 2i. Make sure you're multiplying the top and bottom by the same thing, okay? And make sure that it's the conjugate of the denominator. Don't just square the denominator. Don't do the conjugate of the numerator. It's got to be the conjugate of the denominator. Okay, so now we're multiplying in the numerator. So let's do that. 5 times 7 is 35. And then outers, that will give us 10i. Inners, 7i. And then last, 2i squared. Okay, down below, 7 times 7 is 49. Our outers are 14i. Our inners are minus 14i. Those will add up to 0, like before. And then we'll have minus 4i squared. Okay. All right, so now let's clean up this top part. 35 plus 2i squared. That 2i squared is going to end up being a negative 2 because the I squared is negative 1. 35 minus 2 is 33. And then we'll have 17i. All right, down below, our minus 4i squared, that's negative 4 times negative 1. That'll turn into a plus 4. 49 plus 4 is 53. And then our 14i minus 14i add up to 0. So we'll end up with 33 53rds plus 17 53rds I. Okay, and that does it for division. Division is not something we need very often, but that device of multiplying the numerator and denominator by the conjugate is really helpful. Okay, almost finished. We have two more things essentially to do. So the next thing is to look at something called the powers of I. So we've seen how to do addition, subtraction, multiplication, and division. What we want to do next is see about raising I, just I, up to powers. So we know from the definition that I squared is -1. If we continue multiplying by I, take I cubed will be I times I squared. And then I squared is -1, so we'll get minus I. I to the fourth power will be I squared times itself. Each I squared is worth -1. -1 times -1, +1. Okay, so using that same thinking, let's continue. I to the fifth power will be I times I to the fourth power. I know that I to the fourth power is 1, so this will give us I times 1, or just I. For I to the sixth power, we can look at this as I to the fourth power times I squared. We know that I to the fourth power is 1, and I squared is -1. 1 times -1 is -1. So take a look at this pattern. We have -1, well, I, then -1, negative I, then 1, back to I again, -1. The next one will be -I, and then back to 1 again. It turns out that when you raise I up to a power, you get one of 4 answers. I, -1, -I missed one, I1, -I, and -1. All right, so you get 4 possible answers depending on what the exponent is. So a way to visualize that is through this cycle. So depending on what the remainder is, when you look at the exponent divided by 4, that will tell you what the value is. In other words, if you take the exponent and divide through by 4 and look at the remainder, if you get a remainder of 0, it will be 1, a remainder of 1, it will be I, remainder of 2, it'll be -1, remainder of 3, it'll be minus I. So often people find that a little bit confusing, so I have another way of showing you what that's going to end up being. And so we're going to do that right here. We're going to do a couple of examples. We'll have I to the 23rd power first. So what you want to do is think about what is a multiple of 4 that is less than 23. But what is the biggest one that is less than 23? Not 8, okay? How many times can you add 4s together and have it come out under 23? So the biggest multiple of 4 that's less than 23 would be 20, right? So we're going to use our knowledge of exponents and write that as I to the 20th power times I cubed. Okay, and so what we used there was an exponent rule that says x raised to the a power times x raised to the b power. You'd add the exponents, right? That's the exponent rule I'm using here. So the thing is, we're going to use now another exponent rule that says if you raise a power to a power, that you would multiply those two exponents together. So I'm going to use that to rewrite this I to the 20th as I to the 4th power raised to the 5th power. Why would I do that? Because we know that I to the 4th power is equal to 1, so we can rewrite our I to the 4th power as a 1. Our I cubed we knew was minus I, so we'll end up with just minus I for an answer. Okay, let's try that again. I raised to the 61st power, multiple of 4 that is less than 61 would be 60. So I'm going to write that as I raised to the 60th power times I. And then I to the 60th power, that will be I to the 4th power raised to the 15th power times an I. The I to the 4th power is a 1. We have 1 to the 15th power times I, and that will just be I. So this isn't something that we run across very often, but it is handy. This, I think, is pretty interesting how you can keep multiplying raising numbers to powers and it doesn't keep getting bigger. If you think about raising like some other number to powers, you end up getting bigger and bigger answers, right? But here you just get one of 4 possible answers, and they just cycle through those 4 different possible answers, depending on what the exponent is. So that's pretty neat. If you have any questions about that raising an I to a power, let me know. In the meantime, we're going to move on and just evaluate a function at a complex number. And so we want to see that this is the same as the way we've always evaluated our functions before. Our function f is 4x squared minus 2x plus 3. And we're going to find f of negative 1 plus 2i. So f of negative 1 plus 2i, we're going to put the negative 1 plus 2i in place of all the x's. Okay, and this is a good way to practice all the skills with addition and multiplication of complex numbers that we just saw. So first thing I'm going to do is this exponent. I need negative 1 plus 2i squared. So I'm going to do that over here on my scratch paper. So we'll have negative 1 plus 2i times negative 1 plus 2i. If you know the perfect square trinomial formula, that will help you here and save you a little time, but I'm just going to go through the steps for you the long way here. So negative 1 times negative 1 is 1. For the outers, we'll have minus 2i. The inners minus another 2i. And then for the lasts, 4i squared. Okay, so we'll have 1 minus 4i. And then 4i squared will be negative 4. So negative 3 minus 4i. That will be our product. So let me put that in here. So we have 4 times negative 3 minus 4i. I'm just going to recopy the rest, and we'll do that in a later step. Okay. So now we have to distribute. So we're going to distribute the 4 in our first complex number, and then the negative 2 in the second part. 4 times negative 3 is negative 12. We'll have minus 16i. Negative 2 times negative 1 is positive 2. Then we'll have minus 4i. And then finally plus 3. Okay, almost done. So now we're going to combine the real parts. 2 plus 3 is 5. 5 minus 12 is negative 7. And then complex or imaginary parts, 16i and negative 16i and negative 4i is negative 20i. All right, so that was the steps to evaluate a function at a complex number. You saw that we could do it basically the way we would have done it if it was a real number. It's just that there's a little more to it because the numbers themselves are complex. This type of problem also is a nice way to practice at doing addition and multiplication with complex numbers. That takes us to the end of our section on complex numbers. In the next section, we'll go on to working with quadratic functions, and we'll get a little practice of working with complex numbers there. As always, let me know if you have any questions, and have a great day.